So as I was saying, Isaac Newton was um, one of the people who is mostly associated with the study of calculus. Newton and another mathematician whose name I have difficulty pronouncing, but I'll write it for you. Um, they're credited with creating calculus in the um 18th, yeah, the 18th century, meaning 1700s. So all of these problems that I mentioned, the tangent line problem, the velocity and acceleration problem, the max and minimum problem, or the area problem, all of them can be used to introduce the idea of what a derivative is, which is what we are eventually going to be talking about. Now, as far as the tangent problem is concerned, if we had a circle, let's say we had a circle center right here, and we made a diagonal from the radius. Let's say this is the radius, so we make a diagonal here. We make a this makes a right degree angle here. Then we can create a tangent line at this point, and that tangent line will be the line going like this, that just hits this green point right here. So that blue line is what we call the tangent line. The tangent line, we think about it as hitting, so let's say hits the circle, in this case circle, at exactly one point. Whereas if you remember from earlier, when we had a secant line, the secant line, for example, a secant line going here went through 2 points on our graph or our circle. So that is one of the main, or really the main difference between the tangent line and the secant line. Now for circles, this is not a difficult problem to solve, not that difficult problem anyway to solve. However, for a general curve, the problem is more difficult. So for circles, this is not too much of a problem. However, for general equations or general graphs, this becomes more complicated. Let me give you a couple of examples. So let's say you had a parabola kind of going like this. If I wanted to find out what the equation of the line going through this point up here is, then I'll have to do some work. This is going to be a constant line. It's a horizontal line, so that will just be the equation y equals f of x, where x is that particular point. Let's say it's here. So that line corresponds to this graph. Now for something that looks like this, if I was to look at the tangent line of the point here, and let's say that tangent line goes like this, then now this becomes much more challenging to find, because you have to find the slope of this line that's passing and just touching this one single point there. Or what if we have something like this? Let's see, if we had something like this. Yeah, like that. And you wanted to find out the line tangent to this point right here. Well, you can approach it this way. Oh, I just messed that up. This way. And as you can see, that's also going to be very difficult to find as well. So actually getting the tangent line, it's not easy. In the beginning of the semester, uh, we've began estimating the secant lines. And remember that we began doing this estimation by using the slope formula. So we derived it by saying the difference in y divided by the difference in x is the slope formula. Well, the graph of a secant line, for example, which is what we use to estimate the tangent line, for a graph, let's say, that looks like this, comes from this slope formula. So the function that we're going to be playing around with today for the tangent line will come from some manipulations of this slope formula. So let's assume that you have a point here. This point, let's say this is point C, and right here you have the output f of c, so this is c f of c as the coordinate pair. When we were evaluating or finding what the slope of the secant line was, we will pick another point on the line, let's say that red point up there, and what we used to do is, well, we found out what the coordinates were, and then we used the slope formula to get the slope of the secant line. Well, let's assume that we are moving, and I'm going to be very careful with this, we're moving in this direction, right? So we are adding to this c. Let me just add some numbers so you can see what's happening. So let's say you had a function that looks like this, and this is 3, let's say here's 5. If this is the point, let's say this is 3, 1, right here, this is point 3, 1. Then when I move to the right to 5, I'm adding 2. So this is really, let's say this is a point 5, 2 up here. Let's say that's 5, 2. I could express this point as 5, 2, but I could also express this point as 3 plus 2 on the x coordinate, and f of 3 plus 2 in the y coordinate. Okay, so this is the same way of expressing this by doing this. So that's what's going to be happening here. So here, this distance, I'm adding some x distance. So remember, the change in x we were describing as delta x. That triangle, again, is the Greek letter word delta. And in this class, for the most part, we're going to use it to refer to change. So this point right here really corresponds to c plus delta x. And then the output, much like we did here, is going to be f of c plus delta x. I'm going to write it, I'm writing it in this form because this is how we get the general formula. So if we wanted to get the equation of a secant, of the slope of the secant line, then what we have here, and I'm going to distinguish it by writing secant in the bottom here in the subscript, we have y2 minus y1 divided by x2 minus x1. That's how we find the slope. But my secant line is precisely this line that goes through these 2 points. And that line has the point c plus delta x, comma f of c plus delta x, and c comma f of x. So what I'm going to do is I'm going to say, okay, let's this be y2, which makes this be my x1, and that will force this to be my y1 and this my x1. If that's the case, then if I follow this formula here, then that means that y2 is going to become this f of c plus delta x minus, this from the formula, y1, well, y1 is just f of x, I get that from here, divided by x2. x2 is c plus delta x, and I'm going to put that in parentheses, minus x1. Well, x1 is just c, so minus c. And again, these are arbitrary points. This is how we are deriving the slope of the secant line. And now we just have to do some simplification. So if we simplify this, a little bit, we have in the numerator, there's nothing to simplify. This is just f of c plus delta x minus f of x. There's nothing to simplify because we don't have like terms in here. In the denominator, however, we do have a like term. This is c minus c, so they cancel out. And you're just left with delta x. And this right-hand side is what in pre-calculus, if you took pre-calculus at Lehman, this should bring some memories back. This is called the difference quotient. We did this also in our review on the first week of classes. So this is the so-called difference quotient. Here the denominator delta x is the change in x, and the numerator delta y is the change in y. So here the denominator delta x is again the change in x, and the numerator delta y, well, delta y here is now equal to f of c plus delta x minus f of x is the change in y, in the y variable. Now, the beauty of this definition is that we can obtain more and more accurate slopes for the tangent line by choosing points that get closer and closer to the point in question. So for example, let's say we're looking at a graph like this, right? And we begin with a point here that we want to find the equation of the tangent line, and we make another point here, and we make a secant line. Well, that's going to have some slope. But then we could take the same graph, the same point, and then we could bring in an estimate with a point closer. And this is going to be a more accurate representation of the tangent line. And the closer and closer you get, on the x-axis to the particular point, I'll call them C. The closer and closer you get to that C value, the closer you're getting to this value up here. Because remember, the output values, let's say this is c plus delta x, the output values are getting closer and closer to f of c. And if you notice, this is the way that we define the limit, or very similar to the way that we define the limit. So the closer and closer you get from the left side as well, you're getting closer and closer to f of c as well. So if you're here, if you're looking at values right here, then your output values are very close to c, which means that you're getting very close to the slope. You're getting a very good approximation of the slope of the tangent line at c. So let me give you the actual definition of the tangent line with slope m. So this is a tangent line with slope m. And that is, if f is defined on an open interval containing c, so an interval containing c, and if the limit sorry about that. And if the limit as delta x approaches 0 of delta y over delta x equals the limit as delta x goes to 0 of f of c plus delta x minus f of c divided by delta x equals m. If this limit exists, then the line passing through c and f of c, then the line passing through the point C and f of C, with slope m is a tangent line to the graph of f at the point C f of C. Just a tangent line to the graph of f of x at the point C f of C. So here what we're saying is that if you have a function f that's defined on any open interval, it could be the whole entire real number line. If the limit exists, and this limit is some number m, could be positive, negative, or 0, then the line that passes through that particular point with the slope m is the line of the tangent, is the graph of the tangent line of f. So for example, let's say you take the limit as delta x goes to 0 at C f of C, and you get that slope is 1. Then now that you have the slope 1 and you know what f of C and C are, then using this these two pieces of information, you could use this formula, and you could actually write down the equation of the tangent line, because you know what m is, you clearly know what C and f of C are. So f of C will take the place of y1, and x1 you plug in C for that, and you'll have the equation of a line. And that equation, this equation of the line, will be precisely the equation of the tangent line at the particular point. All right, so let's do an example. Let's find the slope of the graph of f of x equals 2x minus 3 at the point 2, 1. Well, to find the slope of the graph of f of x when c equals 2, we can apply the formula from above. So that says to take the limit as delta x goes to 0 of c plus delta x minus f of c divided by delta x. Well, we don't know what delta x is, but we do know what c is. Here c is 2. So that's our input value. That's our x value. So let's see. That is limit. That's delta x goes to 0 of f of x. It's the same thing as the limit. That's delta x goes to 0. What is f of x? F of x is 2x minus 3. 2x minus 3. But now if we were to substitute f of x with f of with the formula up here, then that means that the limit is actually equal to f of c plus delta x minus f of c over delta x. So we have the same thing as the limit. Delta x goes to 0 of f of, in this case again, c is 2, so 2 plus delta x minus f of 2 divided by delta x. That's from the formula. So the formula says take the value of c, which is the value of the independent variable of the x, plug it in, and for the first one we also plug in this plus c. Okay, so what is f? F is 2x minus 3. So that means that what we're really doing is we're taking the limit as delta x goes to 0 of 2. Wherever I see an x, I'm going to put in 2x plus delta x. That's what it means to evaluate the function at that particular point. And please bear with me because my whiteboard just crashed. open it. All right. And I guess I'll have to rewrite this again. Find the slope of f of x equals 2x plus 3 at the point 2, 1. And what I had written down was this. Limit as delta x goes to 0 of f of x is the same thing as limit as delta x goes to 0 of 2x plus 3, which is the same thing as the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 divided by delta x. Now what I just said is we're going to take this function and we're going to evaluate it at this value and then at this value. So what we really have is limit as delta x goes to 0 of 2 times 2 plus delta x plus 3. So what I just wrote here is 2x plus 3, and this is replacing the x. Okay, so that's what it means to evaluate the function at that value. Minus, this minus comes from the formula right up here, f of 2. Well, f of 2 is just, again, this function evaluated at the value of 2. So that's just 2 times 2 plus 3. So what did I do? In the 2x plus 3, I substituted x with 2. All divided now by delta x. We still have this division right here. Okay, so we still haven't taken the limit, so we'll carry that down. So the limit as delta x goes to 0. Now we could FOIL a little bit, so we could expand this. 2 times 2, last time I checked, is 4. 2 plus delta x is just 2 delta x, and then plus 3. That's on that first bracket. Minus, well, 2 times 2 is 4, so minus 4, and then the 3 we carry over, so minus 3, all divided by delta x. Oh, actually, hold on. I just realized this is supposed to be at 2x minus 3, not plus 3. Just when the screen crashed, I didn't notice that change. Okay, this just froze. And it crashed once more. Okay, maybe I will be changing this app and actually editing these videos. This is getting ridiculous. Next time I'll try to use the OneNote app. Maybe that will not crash so much. Just hope that everything stays. And so yeah, my apologies for that. Alright, looks like not much has been lost. It's supposed to be minus 3, not plus 3. I mean, it doesn't matter whether I do plus or minus. Either way, I'll get the same solution for this particular problem. Alright, so minus and minus, this should be a plus, and this one in here should be a minus. Because the original that I gave was 2x minus 3. Alright, so again, let's keep going. So we have limit as delta x goes to 0 of, well, 4 minus 3, that is 1. So this is 1 plus 2 delta x. And then minus 4 plus 3 is minus 1 divided by delta x. 1 minus 1 is 0, so we just have limit as delta x goes to 0 of 2 delta x divided by delta x. Now this is important, this next step. Notice that delta x is not 0 because we are approaching it we're going towards 0. So we are, if we're in the number line, 0 is here. We're going from the right and we're going from the left. So delta x is not 0. And because delta x is not 0, we actually get to cancel it out. Now if we take the limit as delta x goes to 0 of, instead of 2 delta x over delta x, of simply 2. But remember, the limit of a constant is just a constant. So limit as delta x goes to 0 of 2 is just 2. So what does this mean? So we have that the slope of f at 2, 1 is m equals 2, which is what we expected. Maybe you didn't expect this, but I did. And the reason why I expected that is because the function that we were dealing with, f of x equals 2x minus 3, it's a line, it's a linear function. And remember, the linear equation of the forms y equals mx plus b, the m is the slope, so we know what the slope is coming off the bat. And if you were to find the tangent line at this point, you know, the line that's tangent to that point is the line itself. It's the only line that passes through that point, and just that point is this line itself. In that direction, you know. Can't go like this, you know, not allowed. So we in fact have what we expected to get. So for a line, we get what we expect, which means that this definition of slope agrees with our old definition of slope. Note, this new definition of slope agrees with our old definition of slope. And this is actually very good that it does. Right? Well, how about if we have a graph that is non-linear? You know, what if you have a parabola or something that looks like this? We haven't really ever, at least not in any of your classes so far, discussed how you find the slope of a line right here, tangent here. I just told you about this one. In this particular case, you may be able to find it because that's a horizontal line. But for these other lines, like up here as well, a line that goes through there, they're very difficult to find. Well, not very difficult, but so relative. Eventually, you get very good at finding the slope of these lines using calculus. So let's do another example, just so you can see what I mean by eventually they'll get very easy, or easy enough. So let's find the slope of the tangent line of f of x. So find slope of tangent lines of f of x equals x squared plus 1 at the point 0, 1. Okay, so let's see what happens. So at 0, 1, what do we have? Well, we still have to use our new definition of the limit. So that's limit as delta x goes to 0 of f of x. In this case, f of x is x squared plus 1. This is, again, limit as delta x goes to 0 of x squared plus 1. But I'm right away going to substitute using the formula from before. So this is going to be I'll write the formula first. So this is going to be f of c plus delta x minus f of c divided by delta x. We know what c is. C is the x value, so that's just 0. So it's going to be the limit as delta x goes to 0 of f of 0 plus delta x minus f of 0 divided by delta x. And now all I have to do is, or all we have to do is substitute. Remember that the function is x squared plus 1. And you're substituting in 0 plus delta x into it, and then 0 again. So here we'll have, since x squared plus 1 is going to be 0 plus delta x squared plus 1 minus 0 squared plus 1 divided by delta x. Okay. So now what? Now we can simply do the following. We'll do we could square this, so 0 plus delta x is just delta x squared is just going to be delta x squared. So this right here just becomes delta x squared plus 1 minus, well, 0, 0, 0, so minus 1 divided by delta x. Now notice that the 1's will cancel out because 1 minus 1 is 0, so we have limit as delta x goes to 0 of delta x squared over delta x. But remember again, delta x is not 0, so this allows us to cancel, and we're left with limit as delta x goes to 0 of just delta x. And because this is, you could think of delta x as just being x, it's just a variable, so we can simply substitute, because if you think of it as a variable, this is just a monomial or a polynomial, and we know that polynomials are continuous at all points in the domain, so there's no issue in the domain, so we could just plug in, and this is going to be 0 when you plug in. So we have that at the point 0, 1, the slope is 0. Now, what if we were to do this problem, make this problem a little bit more interesting? The same slope, but what about the point? If we were to find the slope of the tangent line at the point, let's see, negative 1, 2. Well, if you were to find the slope of the tangent line at the point negative 1, 2, then again you're dealing with the same function, because I haven't changed it, and that was x squared plus 1. But now instead of plugging in 0, we're going to be plugging in negative 1. So we have delta x goes to 0 of f of minus 1 plus delta x minus f of minus 1 over delta x. Please keep in mind you are not distributing this negative sign into the input. Please don't do that. I've seen students do that. That is what we call wrong. This negative sign is from the formula. So anyway, we have limit of as delta x goes to 0 of, remember the equation was x squared plus 1, so now we will do minus 1 plus delta x squared plus 1 minus f of minus 1, which is going to be minus 1 squared plus 1, all divided by delta x. Typically, when you have a problem like this, I suggest working on the numerator in separate stages, meaning first do some scrap work on the side, because it's going to get complicated, and the difficulty of this problem is not the calculus. The difficulty is just keeping track of the function that you're dealt with, because eventually you're going to have a very long polynomial function or a rational function, and it does become a lot more tricky to just keep track of what you've done. So I suggest first work on one side of the function. For example, I'm going to work first on the minus 1 plus delta x squared plus 1, and then in the bottom I'm just going to work with the other one, which is minus 1 squared plus 1. So that's my suggestion to you. Do this on the side and then put it together. When you square this, you're basically doing minus 1. If you don't remember, you're doing minus 1 plus delta x times minus 1 plus delta x plus 1. So you're going to FOIL this. So minus 1 and minus 1 minus 1 times minus 1 is just 1. Minus 1 times delta x is just minus delta x. And delta x times minus 1 is just minus delta x. And then delta x times delta x is delta x squared. And then you still have the 1 carried over. 1 plus 1 is 2. Minus delta x plus minus delta x is minus 2 delta x. And you just carry the delta x squared. The other one is much easier. This is going to be negative 1 squared is just 1. 1 plus 1 is 2. Right. It is useful if you remember from college algebra the following, and that is that a plus b squared is the same thing as a squared plus 2ab plus b squared. That's something very useful. Notice that this is the case here. This minus 1 squared is 1. Then ab is going to be whatchamacallit, a here was negative 1, b was delta x, so it's going to be 2 times minus 1 times delta x, which is what we have here, negative 2 delta x, and then finally b squared is just delta x squared. So you can see that, that always works when you have a binomial being squared. So that's good to keep in mind. In any case, we can keep on going now that we have completed our scrap work. So we have limit as delta x goes to 0 of this. And what is this? Well, we just figure out that the top is going to be 2 minus 2 delta x plus delta x squared. This is this first one. We still have the negative sign. I haven't distributed that. This second part is just 2. I could have just written minus 2, but I want to emphasize we haven't distributed the negative sign. So now let's simplify this a little bit more. So this is the limit as delta x goes to 0. The 2's are going to cancel because this is 2 minus 2. So they go away. And we're left with negative 2 delta x plus delta x squared divided by delta x. Now notice that in the numerator we have delta x in both of the terms, which means that we can use your favorite word in math, the F word. We could factor. So we could take out 1 delta x from the top, and we're left with just minus 2 plus delta x in the numerator, and in the denominator we still have delta x. Once again, since we are going to 0, we can say that delta x is not actually equal to 0, and this allows us to cancel. And we have limit as delta x goes to 0 of minus 2 plus delta x. Finally, again, this is a polynomial. This is the same thing. You could think of that being minus 2 plus x. This is continuous at all points in its domain. And by our limit laws, we can simply just use the substitution method and plug in 0. So I'm going to plug in 0 for delta x, but minus 2 plus 0 is just minus 2. So we have the slope of the tangent line at the point, what's the point that we're dealing with, negative 1, 2? Yeah, negative 1, 2. At negative 1, comma 2 is m equals negative 2. Now I didn't do it for the other problem, so I'm going to do it for this one. If you were need to find the actual tangent line, then all you have to do is again use the slope point formula, which is this. This is your x1 value, this is your y1 value. So we have y minus 2 equals m we know is minus 2, and x minus minus 1. So we have y equals minus 2x plus 1 plus 2, so that's y equals minus 2x plus 3. I just move the 2 to the other side and then add it, and I have a mistake here because I'm distributing this, so this is minus 2 plus 2, which is 0, so it's just minus 2x. If you distribute the minus 2 to that plus 1, you just get minus 2, and then you're adding this 2 over, so this is going to be 0. So this is going to be the equation of the tangent line at that particular point. I may be able to show you this later on using GeoGebra. This leads us to probably the crucial point of the whole calculus class. So this process of finding the slope of the tangent line leads us to the crucial part of calculus. I'll say of calculus 1. The limit is used to describe or define, actually I should say, not describe, define the slope of the tangent line it's also used to define the derivative. We call this differentiation. It's supposed to be an A down there. So let me define formally for you the most important tool that we will use in the whole semester, which is the derivative of function. So definition of the derivative function. Okay, so the derivative of f at x, at a point x, is given by the following. F of x equals limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x, provided that the limit exists. And for all x for which the limit exists, for all x for which the limit exists, f prime is a function of f of x. So notice here we have two things going on. I'm going to change the color of this. So the derivative of f, the function f, at a point x is f prime of x. So what I want you to note is that the derivative of function is also a function. In particular, it is also a function of x. Now this new function gives us the slope of the tangent line to the graph f at that particular point. So this new function gives us the slope of the tangent line to the graph of f at the point x, f of x. Obviously provided that there's a tangent line at that point. Now the process of finding the derivative of a function is called differentiation. So this process of finding the derivative function is called differentiation. And something important to note is that a function is differentiable at x if its derivative exists. At the point x, and we say a function is differentiable on an interval, open interval at that, AB, if the derivative, or if the function is differentiable at every x in that interval, an interval AB, if the function is differentiable for all points on that interval. Now, this notation that I just used, this right here, this is the notation of the derivative that I will use. This is read as f prime of x. Okay, so we say f prime of x. Sometimes you may just see it as f prime. Basically, when you put this apostrophe on top, we just read that as prime. We say it's prime. There are other ways that you may see the derivative be written down as far as notation is concerned. Different books use different notation. Different people that you may see on YouTube use different notations. So it's important that you are familiar with all of them, or at least the most common ones. So I'll just write all of them down. So the one that I'll use the most is going to be f prime of x. You may also see dy dx. This is very useful when you do differential equations and when you're doing when you're taking partial derivatives as well, which we may get to speak a little bit about those in the future. This is y prime. Notice that this looks like a 1, but it's not. That's a bit annoying. You'll get used to it though. D dx of f of x is another notation that you may see used a lot as well. And another one that you may not see used, at least by me, often is this dx of y. You may see this in your calculus 2 class when discussing something called the shell method for something called integration. You may see this notation be used because it is useful to express the problem in that way when you get there, if and when you get there. I mentioned this in passing, but the notation, this notation is read as the derivative of y with respect to x. Or simply, which is what I will say often, dy dx. Now, I'm saying with respect to x because it is possible to take derivatives with respect to other variables. So when you get into more advanced classes, you may see functions, and I'll just mention this in passing, in terms of more than one variable, like, you know, like this, and you may have something like 2xy plus 3 minus cosine of y, let's say. This is a perfectly fine function, and if you were to take the derivative of this, you will have to specify which variable you're taking the derivative with respect to. So when you get to like a vector calculus class, this notation is often preferred. I guess one more notation that I should use, I don't use this almost ever, which is like this. Delta, this is supposed to be delta, the Greek letter word delta as well. It's like a lowercase. This is dy dx. So you may also see it like that. I rarely will use that. In fact, I probably will never use that in this class. Let's do a couple of examples of this.